Okay, so the first question is linked to one of the demonstrations and the experiments we did, which is you've got your microwave oven and then you're going to have a question on the chocolate in it and what happens to it. But you've got your microwave transmitter and your oven wall. So before you take the turntable out, what they're thinking about, how is a stationary wave formed in the microwave oven? So very much the same way that any stationary waves formed, is you generally think about the wave being reflected. And then you think about the wave going on top of itself, and we call that superposing. It's really key at this point you don't say superimpose, because that's not the same as superposing. Superposing is thinking about when the wave adds together. So when you get 2 points at a maximum added together, you would get your constructive interference, or 2 points, opposite point of the wave, you would get your destructive interference. But they are really quite hot on checking, the difference between superposing and superimposing. In general, I don't think there's anywhere in the specification where you would need to use the word superimpose. So always just remember that it's going to be superpose. Then the next question is thinking about you've got the turntable taken out, just as we did in our practical, and putting the chocolate in there. So then turning on the oven for a minute and then thinking about what happens. So it then says suggest why the chocolate only melts in the positions shown. So you're thinking about why would this have melted here? So obviously it's only going to melt at the points where the energy is at a maximum. And that would mean, therefore, that the amplitude was a maximum. So either one of those would have got you your first mark. But then thinking therefore, if you think about your waves on a string, so if you had your wave like this, which then reflected back, you're then going to have 3 points of antinodes, which are going to be maximum energy, which would be where your chocolate melted at. So you would then think that the chocolate melts at antinodes. Okay, so the next question is thinking about making suitable measurements to figure out the frequency of the microwaves used by the oven. So what you then need to think about is measuring your distance between the nodes, or antinodes in this case, and you need to think about using all of them, because obviously if you use half, your error is going to be double. So I think it's about, I'm going to go with 11.5 centimetres. So if I put the distance between the 2 antinodes is 11.5 centimetres, which is equal to 0.115 metres. And then that is obviously going to be equal to our wavelength, because thinking about the full wavelength, 2 antinodes would be 2 amplitudes, which would be, 2 maximums, which would be our whole wavelength. So thinking about if you've got your wave and you've got your 2 points of, so you would have one antinode, another antinode, another antinode, from the fact that you've got your standing wave, and so that would be the distance of the wavelength. So you then use your speed is frequency times wavelength. So our frequency is going to be 3 times 10 to the 8 divided by 0.115 meters. And if we use our calculator, 3 times 10 to the 8, we're going to divide that by 0.115 meters, and that gives us our answer. And I use my engineering button to give us 2.61 times 10 to the 9 hertz. So this one says, explain why most microwaves contain a rotating turntable on which the food is placed during cooking. So you need to think about what you would want ideally was for the antinodes, or the maximums, to be changing or constantly changing during cooking, to make sure that all of the food is heated up. So I would say antinode continually changing during cooking. To heat all food.